Okay, welcome back everyone. In the next few videos, we're going to start talking about angular momentum. So this is the last of the analogs that we're going to study for now, analogs between linear motion and rotational motion. But this is a very important one. And so what we're trying to figure out is, first of all, what's the angular momentum of a rotating object? And then, how can a particle moving in a straight line actually have angular momentum? So before we do that, we're going to do one more example problem involving rotation. So we're going to have a hollow sphere rolling down a ramp, and we want to figure out the translational speed at the bottom and the angular speed. See, we want v and omega. Okay? So we're going to set this up really quickly. We'll do energy for this. So this means that we have a height of h, and this will be a length of L and theta. So that means that h is going to be L sine theta. So using energy, E initial is equal to E final. And what we'll have is that mgh, which is L sine theta, is going to be equal to the rotational kinetic energy. And because it's a hollow sphere, okay, all of the mass will be on the outside. So it's just going to be mr squared. And omega squared will be v squared over r squared. And then kinetic energy will be 1/2 m v squared. Okay, so m's cancel, and we'll get gl sine theta is equal to v squared. Okay, so v is going to be equal to square root of gl sine theta. And then to get the angular speed, well, that's omega is equal to v over r. And then we just plug that in. Okay, so we'll just have 1 over r root gl sine theta. So nothing too crazy. All right, so now let's talk about angular momentum. So it's a quantity that tells us how hard it is to change the rotational motion of a spinning body. And you might remember that linear momentum is the same thing, but for objects moving in a straight line. So objects with lots of angular momentum are hard to stop spinning or to turn. And that means that they have great orientational stability. Okay, so we'll talk more about what that means in a little bit. So for a particle, if you know the momentum, you calculate the angular momentum with the equation L equals R cross P. L is the angular momentum, R is the distance from the particle to the point of rotation, and P is the linear momentum. So we want to also be sure to write out that we can calculate, the magnitude of this, because it is a cross product, by taking the magnitude of the two vectors times the sine of the angle between them. So if this is R and this is P, then we're looking for this angle right here. Okay? And of course, P, the linear momentum, is just mv. Okay? So we could set up a problem where we're calculating the angular momentum for the revolution of the Earth about the Sun or the Moon about the Earth. Okay? So here's the Sun. Okay? And we'll say that we have the Earth right here, which has a linear momentum p like this, but it's also rotating with an angular momentum omega. And so r would be like this, and the angular momentum for the revolution of the Earth about the Sun would be r cross p. And this is another right-hand rule, and we would find that this particular angular momentum, so call it LA for part A, that would be coming out of the page. our fingers would point in the direction of R, and we would curl the fingers towards the momentum, and then our thumb would give us the direction of angular momentum. Okay, and then if we were going to do the angular momentum of the Earth's rotation itself, that would be I omega, and the Earth is a sphere, so whatever that would be, maybe 2/5 mr squared times omega. Okay, now the moon about the Earth would be kind of similar. We would do a similar calculation as for the Earth about the sun. Okay, so now what we want to do is find the angular momentum for this 2 kilogram particle. And there's two ways of setting this up. What we can do is we can show that the magnitude of this angular momentum is going to be equal to the mass times the speed times the component of the radius, which is perpendicular to that velocity. Okay? And let's just back up a second. So first of all, we have that L is equal to R cross P. Okay? And we said already that R is our fingers, our pointer finger, okay? P is the curl of our fingers, and L is our thumb. Okay? And what we want to do is we want to write for each of these expressions for R and P. Okay, so let's say that we want the angular momentum about the origin. So R would be right here. R would actually be 2I hat minus 2J hat. And then P would be equal to mv. Okay, so m is 2 and v is 3, would be negative 6 j hat. Now we want to set up our cross product, I hat, j hat, k hat, and R and P. So we have 2, negative 2, 0, 0, negative 6, 0. And you're going to notice that basically everything is going to be 0 except for the k hat component. Okay, it's 0 I hat minus 0 j hat plus 2 times negative 6 minus 0 k hat. So negative 12 k hat is the angular momentum, and the units for this is going to be kilogram meters squared per second. Okay, now how do we know that it's negative? Well, check out the right hand rule. Try putting your finger of your right hand in the direction of R, and then try curling your fingers towards V so that you naturally are kind of going like this. You're sort of curling them this way. What you'll notice is that your thumb is pointing into the screen. So the angular momentum is into the screen, and that's in the negative direction. Okay, and if you look at this, you can see that m is 2, v is 3, and r perpendicular is actually 2. So the magnitude of this is 12. Okay, so that's part A. Part B, we want to find the magnitude of the angular momentum about the point x equals 2.0. Okay, now for this is going to be pretty easy. All right, I'm just going to draw this r vector in orange. Okay, so that's r, x is 2.0, because we draw it from our point of rotation to the particle, and because r is parallel to p, this means that the angular momentum will be 0. Okay, so if the momentum is going through the point of rotation, it'll be 0. Otherwise, this equation right here is known as the angular momentum of closest approach. That's because r perpendicular is the closest that the particle gets to the point of rotation. And there's actually a way that you can prove this. You pick a random point and you write r and p in terms of vectors, and there's going to be all sorts of angles and sines and stuff, but they're going to cancel out. Okay. So next time, we're going to talk about the angular momentum of solid objects and conservation of angular momentum.